Right. So I've been spending a lot of time, as Lorena suggested, working on multilingual speech processing problems, and just in the past 3 years or so, I've really been kind of transitioning back into this topic of disability and working on inclusive automatic speech recognition. And so what I'm going to try to do today is to kind of bring together those ideas together with some kind of more speculative sort of theoretical ideas. I want to start out with this concept of Zipf's law, which you've all heard of. It wasn't invented by Zipf, but he was a linguist who studied it in the first part of the 20th century, who noticed that most of the words that you hear in any given day are words that you've never heard before, or that you rarely hear. And this was considered sort of the unsolvable problem in speech processing in the late 20th century, and until suddenly it was solved. And I want to sort of use that as an analogy for a lot of the problems that we deal in making speech technology work for people for whom it doesn't work. Because this idea of power law distributions is not unique to language. It's actually endemic to social constructs. And one of those social constructs is ethnicity. Another of those social constructs is disability. I want to argue that even disability is a social construct, and that therefore we can draw important lessons for dealing with disability by studying the way in which we solved Zipf's law for speech processing. So let me first of all remind you what Zipf's law is. This is an image from Wikipedia. Basically the way that it's sometimes phrased is that the majority of words are rare. Right, that the nth most frequent word in any given text has a frequency which is proportional to 1 over n. And what that means is that in any given text, there are, about half of the words will be the same 10 words over and over again, and the other half of the words will be words that you have never seen in your training corpus at all. This is remarkably true across a wide variety of languages. This is somebody named Sergio Jimenez did this study of 24 different languages, I think, including artificial languages like Esperanto, and found that all of them have this 1 over n distribution of words. And this became really interesting to me, I think, when I read a book called The Black Swan by the guy who predicted the housing market crash in 2008, Nazem Nicholas Taleb. He argues that the reason that we have power law distributions is because of social constructs, because of the dynamics of social organization. He was arguing that that Gaussian distributions and Poisson distributions and exponential distributions occur when a random variable is constructed by a biological dynamic process. By adding together the effects of a lot of different genes, you get something like height or speed or strength, which is distributed in a Gaussian fashion. And he argued that most social constructs don't follow that same dynamic process. Wealth or popularity or the number of sales of your book, right? These are all constructs where the possession of that attribute allows you to get more. If you have money, you can make more money. If you have a lot of readers of your book, then you can get more readers of your book. If you are an author trying to decide what word to use to express a particular concept, the word that you're likely to choose is the more frequent word, because that's the first word that will come to your mind. Right? And so when you have these dynamic processes where already having an attribute allows you to get more of that attribute, then you get these heavy-tailed power law distributions where the vast majority of people have very little money, and then there are a few people who have a lot of money, right? And so this is interesting because in speech processing, most of the constructs that we deal with are actually social constructs, and so we shouldn't be surprised that power law distributions take up a lot of the things that we want to study, and so that we called that a problem in the 20th century. We said that this means that speech recognition will never be solved, because no matter how large your training corpus is, it will never have all of the words that you expect to find in your test corpus. I credit Mitch Marcus for pointing out that this is not just a problem, this is also a solution, because it means, number 3, out of vocabulary words, there will always be words that you've never seen before. But Mitch Marcus also pointed out this means that there are a small number of words that you see all the time. And so if you have some crazy new idea that you have no idea whether it will work or not, you can test it on the easy cases, and you can be guaranteed that those easy cases will take up a large fraction of your data. you can say, let me go out and I'll just see if it works on the 50 most frequent words in the English language. That's already a pretty good number of sentences, right? And so we have this actually kind of a three-part distribution that doesn't make sense for Gaussians, but it does make sense for power law distributions. There's a small number of very frequent words that you can test your idea on at very low cost. There's a very, very large number in the middle of infrequent words that you have some hope of being able to model them well, but it takes a huge amount of effort to do so. And then you have these out of vocabulary words that you can't possibly model no matter what you do. And so we have these sort of, it basically takes everything that we do and divides it into three very different problems that often have three very different solutions. So for automatic speech recognition, for example, we can look at this over the decades. This is the ASR word recognition accuracies reported in 4 different papers, one in 1970, one in 1990, one in 2010, one in 2021. And when I was in graduate school, people would ask, what is the accuracy of automatic speech recognition? And I would say 95%. And now if somebody asks me, what is the accuracy of automatic speech recognition? I say 95%. Right? It hasn't changed over those 4 decades. What has changed is the vocabulary size over which we get 95% accuracy. In 1970, the paper by Velichko and Zagriko invented dynamic time warping. They had a vocabulary size of 200 words. And on those 200 words with 2 speakers with clean microphone reading conditions, they were able to get 95% accuracy. So this was a crazy idea. People had been proposing in the United States doing automatic speech recognition by building a model of every single phoneme and then recognizing the phonemes using some kind of rule-based extraction of information from the spectrogram, and then looking up the possible sequences of phonemes that could construct every word. Velichko and Zagriko just said, what the heck, let's just pick the 200 most common words and let's recognize those. And let's treat it as a distance learning problem rather than treating it as a linguistics problem. And they got the best recognition accuracy up to that date, and they introduced the idea of dynamic programming into speech processing, and everything that we've worked on since 1970 is based on that idea. And then there was this long period of time where we had to solve the problem of all of the middle words, right? Because going from 200 words in 1970 over here to maybe Kai-Fu Lee's paper in 1990, where he had 1,000 words, to maybe the opinions of 4 research groups, the hybrid neural net HMM systems that were around 2010, right? We had to go from 200 words to 1,000 to 20,000 words in the switchboard vocabulary. Even by the time you get to 1,000 words, you can't really have a whole word model of every single one of those 1,000 words. You need some way to generalize from the words, from these 200 words to the other 800 words that are less frequent. And so we had to build these methods for generalizing from the 200 frequent words to all of the words that did occur in the training database, but occurred a lot less frequently. And the way that we did that, of course, was by using phonemes or things based on phonemes. We built acoustic models of left to right hidden Markov models, 3-state hidden Markov models, where you could train each of those states using any word in your training corpus that had that particular sequence of 3 phonemes. And then you could generalize it to a word that only occurred in your test corpus that used the same sequence of 3 phonemes. And that allowed us to generalize, to share data across words in order to be able to recognize gradually larger and larger vocabularies over the course of those 50 years. And that works as long as every word that you want to recognize is a word that you know that you might want to recognize. If you can look up that word in a dictionary and find out what phonemes it's composed of, then you can use methods like this to recognize it. But that's not the case for English or for any other standard language. If you want to invent a word in English, write a popular blog post tomorrow and put that word in your popular blog post. And by a week from tomorrow, every teenager in the country will be using your word, right? There's no limit to the number of words in a language. And so this method was never going to solve this problem of recognizing every word in every given text. In order to do that, we had to build effective subword models, and this was recognized for a long time before it was actually implemented. I would identify maybe this paper by Nikolov et al. In 2012 as as effectively showing that subword language models can be used to recognize words that were never seen in the training data or even imagined, right? The words new and company clearly occurred in the training data. Interactive almost certainly occurred in the training data, but it occurred with low frequency. And maybe the word DreamWorks never occurred in the training data, but we had subwords from which it could be composed, to dree and am and whoa and irks. Right, those were subwords that did occur in other word combinations in the training data. Notice that the key technical problem here is that you can't really model the probability of this sequence given only the previous two sequences. So we had to get beyond trigrams in order to make this effective. And so this was why maybe end-to-end neural methods were a prerequisite for making this kind of subword modeling effective. We had to have arbitrary length histories in the language model before we could use effective subword language modeling. And in this way, we solved the problem that everybody in the 20th century thought was unsolvable. We can now effectively recognize speech to text in an unlimited vocabulary by building things from subword models.
So you're maybe going to talk about other ways that this problem had been solved before.
Actually, I was using this as a metaphor, and I was going to go on and talk about totally other subjects. So if you want to,
okay, no, that's fine.
Okay, all right, yeah.
I was just going to say that it's not like the problem was suddenly solved in 2012. Like people backed off from word models to character models, or when they were doing neural stuff, they did spelling based. They regularized embeddings for rare words toward some other embedding based on the spelling.
Yeah,
I think there's a lot of stuff.
I'm definitely oversimplifying. Thanks. Yeah.
Okay.
I mean, you can clearly. I mean, I argued that that this paper was invented because they got rid of that idea of unlimited vocabulary, and they said let's just focus on 200 words, and that was invented because that made the error rate small enough to be useful. And I think it's maybe the end-to-end neural systems around about 2010 that finally made the error rate for things like this small enough to be useful. But certainly people have been working on this for a long time before. All right, so let's use that as what I really want to do is to use this as a metaphor. We have these three very different approaches to automatic speech recognition. One is let's just pick 200 words and recognize those. Another is let's figure out how to generalize information from those 200 words to the other 20,000 words that we know about. And another is who needs words, right? Let's do something totally different. And so I want to say that those are sort of the three different, completely different problem areas that Zipf's law requires. When you have a power law distribution over categories of any kind, then that means that you can test your idea and make it really work by focusing on a very small number of categories that take up about 50% of the tokens. In order to make it useful, you usually need to figure out how to generalize from that small number of categories to a large number of categories that occur less frequently, but for which you can build meaningful models. And then finally, in order to actually, in order to say that you've solved the problem, you need to be able to deal with categories that you've never seen before. And that requires a paradigm shift. That requires you to jump outside of the categories that you've been working with and come up with some other set of categories entirely. So what I want to do for the rest of the talk is to talk about three particular experiments that we've done in my group, applying ideas like this to multilingual and cross-lingual speech recognition. And the middle one is actually in collaboration with Najim and Laureano. And then in the last part of the talk, I'll talk a little bit about this new work that we're doing with disability and with inclusive automatic speech recognition, and try to say where we are in this power law distribution, on the range from early successes to knowledge transfer to paradigm shift. Where are we in dealing with disabilities? So first of all, what does it mean for a speech technology to be multilingual, right? It's easy to say there are 7,000 languages in the world. It's hard to know exactly what that means. So maybe as many as 4,000 of them have writing systems. So if we're talking about doing speech to text, we're already talking about throwing away half of the languages, right? In fact, for most of those 4,000, people who are native speakers of that language are not learning how to read and write in their own language. They're learning how to read and write in the language of some local government. And so for most of those 4,000, we don't really have speech to text, even though the writing system exists. Transcribed speech maybe exists for 700. The largest corpus that I know of is this wilderness corpus published by Carnegie Mellon, which has some speech that's transcribed in 700 languages. The number of languages on which there's actually research is surprisingly small. The ISCA and LREC have put together this LRE map that's trying to keep track of languages on which anybody has written a paper. And as of a couple of years ago, at least, there were only 97 languages that had been registered as actually having been the subject of academic research in any published work. This probably has in any published technology work. This is probably this is probably a registration bias. This is probably has to do with who's actually typing things into the LRE map. But it's remarkable that they went out specifically with the goal of covering 7,000 languages, and as of a year ago, they had covered 97. And that's not surprising when you look at it from a black swan kind of perspective, because the number of native speakers of any given language is one of the most power law distributions. These are the 100 languages with the highest numbers of native speakers, according to Wikipedia. And if you try fitting various exponential and power law models to these data, you find that the best fitting model is 1.44 billion divided by the rank of the language to the negative 1.09. Right, so this is just about as power law as it can get. The number of native speakers of any given language is 1 over the rank of that language. And you can see characteristics of a typical Zipf law, right? The first most frequent language, Mandarin, has about twice as many speakers as the second most spoken language, Spanish. And then after that, it flattens off almost immediately, because 1/3 is not that much less than 1/2. Here, English and Spanish are even closer together than that, and Hindi is closer together. But you can see that it really sort of flattens off to the point where over here, between about 10 and 30, it looks like it's perfectly uniform, right? And you go out here between 50 and 100, between the 50th most spoken language and the 100th most spoken language, we range from 24 million native speakers down to about 7 million native speakers, right? This is, what is this, a factor of 4 maybe. Well, that's larger even than the difference between 50 and 100. But it's very clearly that there's this very, very long tail where if you can do speech to text in Mandarin, well, you've covered 1 billion people. That's great, and you've covered a large plurality of the world's population. But there's still a lot of other people who won't be covered until you get out to language number 500. So yeah, what we mean by monolingual. We can really kind of talk about these three paradigms: the easy early successes, the language transfer, and the out of vocabulary words, as being something like the study of monolingual speech technologies, multilingual speech technologies, and cross-lingual speech technologies. Right? Monolingual methods work for maybe 25 languages or so, those with maybe 50 million native speakers or more, or a lot of money to spend on speech technology. Multilingual methods, where we might try to transfer information from well-resourced languages to under-resourced languages, might eventually work for as many as 700. They don't currently work well for that number. And then eventually, to cover all of the languages with writing systems, we might be able to do that with some kind of cross-lingual methods. Let me talk a little bit about 3 particular experiments that we've done. So actually, this is a little bit out of order. What I'll cover in early success is actually a class project that a few of my students did in spring semester. And what we wanted to do was to ask the question: if you have multilingual, cross-lingual, and monolingual unsupervised pre-training of an ASR, which is better? This was shortly after Facebook published the XLSR 53 parameter set, which is a pre-trained with no labels on more than 50,000 hours of data from 53 languages. And the idea was that this permits you to adapt quickly an ASR to a language that you've never seen before, with far less drop in accuracy than any method that had been previously proposed. And one of my students noticed that almost all of the languages in their study were European languages. This was probably because there's a lot of data on those languages. And so he wanted to see, does it work on non-European languages? So he came up with this paradigm. Let's try pre-training the model on 1,000 hours of untranscribed audio in some non-European language. And let's see, does that work better than XLSR, which has been trained on 50 times as much data from 53 other languages? And just as kind of a straw man base case, we also tried this cross-lingual system, which is pre-trained on English and then fine-tuned to another language. So we had three different pre-training conditions. We also had two different fine-tuning conditions, monolingual and cross-lingual, cross-lingual being the case where it's fine-tuned on the wrong language. The data, we've tried this on every non-European language for which we could come up with at least 1,000 hours of untranscribed audio. And we wound up having to call Bulgarian and Russian as sort of non-Western European languages because we just couldn't find enough non-European languages in which we had that much audio. I think we now have that much audio in Bengali, and he's trying to experiment on that as well. But we tried Arabic, Bulgarian, Japanese, Russian, and Mandarin using the corpora shown here for pre-training and fine-tuning. And the first thing we wanted to do was to make sure that there's nothing wrong with our pre-training algorithm. And so we tried it on English just to make sure that we were getting error rates that were comparable to the error rates that we would get with the parameters that we downloaded from Facebook. And so we downloaded their parameters and fine-tuned it on our English fine-tuning corpus and got 10.9% error rate, did our own pre-training and got 9.9% error rate. Those are different, but we don't know of any reason why they could be different. So we don't believe that's a significant difference. And then maybe this is the main result is that if we try the multilingual, the XLSR system, that actually had the lowest error rates for English, but not actually for any of the other languages. In every other language, the monolingual pre-training outperformed both the XLSR and the cross-lingual. So these cross-lingual error rates are where we pre-train the system using unlabeled English data and then fine-tune it using data in Arabic, Bulgarian, Japanese, Russian, or Mandarin. The multilingual is taking the distributed XLSR parameters and fine-tuning those in these five test languages. And then the monolingual pre-training is where we take unlabeled audio more than 1,000 hours in that language and use that to pre-train the encoder and then fine-tune on additional few hundred hours in that language.
One question. So in the column in the middle, is cross-lingual only using English as the frame?
Right. This is actually cross-lingual for the pre-training. So the English pre-training, but then fine-tuning in the target language. I'm not showing the cross-lingual. Actually, I put on the slide that we did that experiment, but the results were so bad that I had to put them on the numbers on the slide.
Okay. Okay.
Yeah. All of these have over 1,000 hours, you said, right?
Yes.
Do you have any idea of where this might actually shift? Where multilingual and also maybe if you have like 10 hours, I would assume that monolingual would work, right? Do you have an idea of where that threshold is?
We haven't done a lot of experiments there, but if we pre-train on less than 500 hours, we're not getting any benefit. And if we pre-train on more than 1,000, we are. So I think it's actually in the hundreds of hours.
Okay.
I guess it depends also a lot on the pre-trained model and on the language that you're trying to do the cross-lingual. Because I see, for instance, here, obviously, I mean, in Mandarin, for instance, things work worse in cross-lingual, probably because, I don't know, like tonal, like, I don't know that the base model was including any type of tonal information or.
Right. No. Yeah. There are also homonyms in Japanese and Mandarin that are not being very well modeled here because we don't have a separate language model. It's only learning sequence information in the LSTM and the decoder.
Okay.
Actually, not LSTM; it's a transformer in the decoder. So yeah, so the higher numbers in Japanese and Mandarin did really bother the student working on this. He was able to trace them back to the lack of a language model and to the occurrence of homonyms.
Okay. Okay. Thank you.
Yeah. All right, so let me jump past that and talk about a different problem. This is actually, I'm going to be talking about a couple of papers, one of which was Piotr was the first author, Piotr Zalasko, one of which Xiao and Feng was the first author. So these are papers that Najim and Laureano and I have worked together on. And these papers sort of introduced this idea of sort of dividing the problem into three tasks: monolingual, multilingual, and cross-lingual, training. In this case, I'm going to talk about entirely supervised training, where a monolingual recognizer is trained on one language and then tested on the same language. A cross-lingual recognizer is trained on 12 languages and then tested on the 13th language. And this can be done in sort of a 13-fold cross-validation paradigm. So this was tested in these two papers in two different architectures. Both of these were fully supervised. This was a year before the idea of self-supervised learning became de rigueur in speech processing. But in both cases, we have an input spectrogram which goes through a series of encoder layers, and then we have here a self-attention, here a BLSTM. As far as I'm concerned, those are about the same and they get similar accuracies, but then whether we feed that into an HMM or directly into a neural decoder turns out to be consequential. Two types of data were used, global phone and Babel, and this also is quite consequential because global phone is quite a lot cleaner than Babel. And so even though the global phone corpora are an order of magnitude smaller, they still often give better results. In all of these cases, the original text transcripts were converted into IPA using finite state transducer, grapheme to phoneme transducers, and then we took previously existing Babel training recipes and converted them to use IPA transcriptions. Some of the key observations, first of all, for the hybrid system, the monolingual is actually much better than the multilingual case. So that the monolingual system is much better with a hybrid neural net DNN than with a transformer. So the hybrid system actually does have some benefit, but that benefit goes away when we use multilingual training. So all of these corpora are between 10 and 150 hours of training speech data, and that's a small enough data set size that if you train the multilingual, if you train the neural net on the data from all of the languages together, that gives you enough benefit to sort of overcome the benefit of having the same language used in both training and test. The cross-lingual systems perform badly in all cases. So, kind of the interesting first takeaway is that the hybrid system actually is better at some things, but overall, over all of the different criteria for which you might care about, using multilingual training with an end-to-end neural system gives the best result, because that end-to-end neural system is able to take advantage of the multilingual data without becoming trapped in a bad local optimum and trying to reproduce phone sequences that don't make sense in the testing language. And then finally, let me talk about something completely different. How do we deal with languages where we don't have any transcribed speech, which is perhaps most of the languages of the world? And the way that we've been working on this really in the past 3 years or the past 2 years or so is this idea of unsupervised ASR, where you this was maybe I think invented it at NTU, I think in 2018, and of course we're like most others in this field, we're following work at Facebook in 2020 on this subject. If you don't have a transcription for any given audio, but you do have lots of text and lots of audio, then you can treat each of those as a probability density function, and you try to create an ASR, which is just an end-to-end neural network that will reproduce sequences of characters that have the same probability distribution as the sequences of characters that you find in your text corpus, right? And so if you have only 3 or 4 examples, this is not going to work. If you have millions and millions of examples, it may work. As the number of training examples goes to infinity, you can imagine that that you can look at longer and longer sequences and force those longer and longer sequences coming out of the audio to be plausible character sequences, where plausible means that the exact distribution of those character sequences matches the exact distribution that you get out of the text corpus. And that can force the ASR to do something to impose a consistency bias, or similar sounds have to follow similar acoustic patterns, but they also have to generate sequences of characters that match the character sequence. And the question that, as far as I know, a paper that we currently have under development is the first to look at is under what circumstances does that actually work? Can you look at longer and longer sequences of characters? Can you guarantee that you will actually get a correct speech recognizer out of that system? Can you say that yes, looking at long sequences is enough, that we can actually train the ASR such that if it correctly generates that distribution, it is also correctly recognizing the content of that speech. So the paper that Li Ming has written and that I've kind of cross-checked about a third of so far, I'm the bottleneck at this point, it takes the following paradigm. He says, given a corpus of quantized speech sequences, and we're starting with discretized speech, discretized using some kind of k-nearest neighbors, and given a corpus of text sequences, can we take a whole bunch of sequence probabilities, the probability of the nth character in the sequence, and the probability of the 2nth character, and the probability of the lnth character in the sequence, and match those distributions? Does matching those distributions constrain the observation probability matrix sufficiently to actually recover a correct speech recognizer?
So in this case, in your experiments, are you using two completely independent data sets, or are you taking a data set that has already speech and you're taking the transcriptions already and you don't like? Great.
The theory is assuming, well, actually, Li Ming has started to work on the unmatched case as well. So this formula is the matched case, where the distribution of sequences in the acoustic data is exactly the same as the distribution in the text data. In experiments, we've been able to use different corpora in English. In every other language where we've tried to use different corpora, it fails. And I think that what's going on there is that just in English, we have so much data that it's possible to get a gigantic speech corpus and a gigantic text corpus that are both so gigantic that they actually cover the same distribution. And in every other language, I think that the distribution is still corpus specific. And so when we try to cross corpora, it fails. So that's the current status. Right, so this equation is exactly the matched case. This is under the assumption that if you get the matrix O correct, then the sequence distributions for X are the same as the sequence distributions for Y. And the question that Li Ming wanted to answer was, is that sufficient to actually recover the true value of O? And the answer turns out to be yes. If you can assume that the distributions are matched, then that's sufficient to recover O under the condition that the minimum singular value of this probability matrix is larger than some threshold. The threshold is somewhere around 1 over the square root of the length of your HMM, the length of your n-gram, the number of states over which the history matters in the probability, times the size of your alphabet. So basically, the number of distinct character sequences in your language, take the square root of that, and if you can get a probability distribution over your training data that's sufficiently rich that its singular values are above that threshold, then you can learn the data set. And it can be shown that the singular value actually satisfies this criterion under the assumption that these sequences are generated from a random draw from a Markov process. In practice, we found that some corpora that fail this are some corpora that are collected in very low resource languages will be a small set of sentences that are read by a large number of people. And if you have a small set of sentences read by a large number of people, then you have a small number of singular values that are very large, and then all of the other singular values are 0. Right? And so basically what this is saying is that if your training corpus is rich enough, then the singular values of that probability distribution matrix are large enough that it's possible to recover the ASR with actually 0 error in the matched case. We can show theoretically that you can actually recover an ASR with 0 error if, first of all, three kind of difficult to meet conditions. First of all, you have quantized speech signal, and the best possible ASR given that quantization is already 0 error. So if you take your Kepstrel frames and you quantize them to 500 categories, if the mapping from those 500 to the 50 characters is deterministic. If there's no additional error rate just introduced by that mapping. If, second of all, the speech and the text data sets have matched distributions, so that this equation is a true equation. And third of all, if the training data set has sufficient complexity, that is to say that the minimum singular value is larger than some threshold. Under those conditions, at least, it's possible to recover the ASR with zero error from this kind of unsupervised setting. This last condition turns out not to be very difficult. It seems to be true of natural languages. It's only not true of artificial languages or artificially constructed data sets. This middle condition can be relaxed somewhat, and we're working on trying to find ways to relax it. This first condition may not be relaxable. We've tried to find a way to generalize this from discrete speech distributions to continuous speech distributions, and we're not sure yet whether that's possible or not. And so it may be the case that we need to look for better unsupervised methods of quantizing speech in order to make this really effective. But it does seem to be the case that if the optimal ASR for your quantized speech has an error rate of 4%, that it's possible to recover that 4% ASR using unsupervised methods. So this is a theoretical result that is partly supported by empirical data so far, but it has kind of strict conditions. We need to be able to find a large, diverse audio corpus. We need to find a diverse text corpus that's actually reasonably well matched in distribution to the audio corpus. And we don't know yet whether that's actually easier or harder to do than simply getting 1,000 hours of audio in that language and having people write down, hiring people who speak that language to write down the content of that audio corpus. And so sort of from a beyond technology point of view, is this technology actually better than just hiring people in the community? We don't know the answer to that. And so let me jump from that then to the area where we really don't know the answers, and that is, how do we generalize from Zipf's law over words, from Zipf's law over languages, to similar power law distributions over every other kind of social grouping, every other kind of grouping in society. And these other kinds of groupings were brought to attention by articles, including one, for example, on which Jurafsky was a co-author in 2017, that demonstrated that the large published commercial ASRs give lower error rates for white people than for Black people. As some other papers have shown that large commercial ASRs give lower error rates for men than for women. And we might say, of course it does. We've just solved the problem as well as we can. This is the way we solve the problem. And it works as well as it works. But as soon as that idea, we solve the problem as well as we can, that idea works as long as the results of our technology stay in the laboratory. But when the results of our technology actually get deployed at massive scale across society, that starts to become a problem, because basically ASR works well for people who already have a socioeconomic advantage, and therefore it's exacerbating socioeconomic differences in society. The ASR is a productivity tool. If I want information, I can just ask for it, and my smart speaker will give it to me. But that only works if you are part of, if your voice sounds like an audiobook narrator, right? So that ASR has been trained using multilingual LibreSpeech, and therefore that ASR works for people whose voices sound like they might be reading audiobooks, and it doesn't work for the rest of society. And so we're making socioeconomic disparities in society worse by publishing technology of this kind. And this is a real problem. This has been shown for gender, for dialect, for race, for disability, for age. Some of these differences are actually long-standing. Joe Picone showed already in 1991 that ASR trained on TI digits worked significantly worse for people from the American Deep South than for any other group in the population. This paper by Krenicki was actually really interesting in that they tried this 35% is on the Choral corpus, which is a corpus of regional African American languages, which is a very, very difficult corpus to work with. It's oral histories collected from old Black people, basically, and they speak with very strong dialect and very casual, informal style, Carnegie did this really amazing thing of trying to find the most comparable corpus that he could with speakers who are primarily white people. He tried to find oral histories recorded by old people, basically, and showed that even under the case when he made those corpora as comparable as he possibly could, still the African Americans were suffering twice the error rate of the white Americans. Women versus men, it does seem to depend on exactly which corpus you're talking about and exactly which study. In most cases, women have worse error rates than men, but then there are a couple of cases like this Carnegie study where men have worse error rates than women. And it does seem to vary a little bit depending on the ASR. And this may be something that's already solved in the large commercial systems, although I haven't seen results to demonstrate that they've solved this in the large commercial systems. Among age of generally ASR error rates are constant between 20 and 70 years of age. For people over the age of 70, disease and disabilities start to take a toll, and so you start to see a drop in error rates. For people under the age of 20, the error rate kind of goes like this, right? Until when you get to people who are 5 years old, the error rates are well above 50% in most cases. And then finally, one of the things that caused me, the case that caused me to start using the word inclusive here instead of the word fair is the problem of disability. That obviously, if humans have trouble understanding your speech because of a physical disability, then ASR is also going to have trouble understanding your speech. And when I was calling this fair speech recognition, people said, well, but why is it unfair for the ASR to have trouble understanding you when other humans also have trouble? I don't know. It depends on your definition of the word fair. But at the very least, it's undesirable. We would really like it if automatic speech recognition could be useful for people who have physical disabilities. In fact, they might have even more use for ASR as a productivity tool than do the rest of us. Different reasons why it might fail. So far, I've kind of talked about underrepresentation, but some of the other things actually, this, right, the Scottish dialect, right? Scottish people are not underrepresented in technology by a long shot. They're probably far more represented than many other populations. And yet they have a huge difference between the Scottish dialect and most other dialects of English. And that huge difference means that it's harder to transfer knowledge from general American English to Scottish dialect. Intra-group variance. One of the problems with the chorale corpus is that there are very different dialects of African American English. And then finally, intra-individual variance. These things are difficult because most of these categories follow power law distributions. Race, for example, about 70% of Americans are white, about 20% are Black, about 10% are Asian American, about 3% are multiple races, about 1% are American Indian, about 0.3% are Native Hawaiian. This actually fits it. This particular distribution is about evenly divided. The exponential distribution fits it about as well as the power law distribution. But both of these others, regional dialects and second language status, are very clearly power law distributions. So if you look at second language status, most Americans speak English, a large fraction of Americans speak Spanish, and if you want any other native language, there are exactly 1 million such speakers. Right? You can look at French or Vietnamese or Russian or Korean or Arabic or Tagalog or German, and any one of those, there are 1 million Americans who speak that as their first language and speak English as a second language. Right, so all of these are power law distributions, so that means that, that Mitch Marcus's idea about dividing the distribution in three might also be applicable to these problems. We're just starting on this. We clearly have the early success. We clearly have taken all of the people without disabilities who are between the ages of 20 and 70, and we have ASR working for them. How do we transfer knowledge from the hard domains from the easy domains to the hard domains? We don't even know what the similarities and differences are. What are the similarities between the speech of a person with cerebral palsy and the speech of a person without? We don't know in sufficient detail in order to be able to know what kind of knowledge representation will allow us to transfer knowledge. And then finally, we're far away, I think, from being able to talk about breaking the paradigm of disability entirely and building a system that will work for any individual regardless of their disability status. But let me just talk briefly then about this work that we started this year. We started trying to work on disability. Let me skip over the reason why disability is a social construct and just talk about the work that we're doing. We're we've just started this project called the Speech Accessibility Project, where what we're trying to do basically is we're going out and recording. We're going to try to recruit large groups of people with different named disabilities. We're starting this year with Parkinson's disease, and we're working with LSVT, the Lee Silverman Voice Therapy Advocacy Organization. But the primary goal of the project, I sometimes joke, but it's not really a joke, that the main research here is IRB research. How do we actually guarantee protections to the participants that will be sufficient for them to be willing to contribute data, while also being sufficient to allow us to distribute the data to researchers who want it. And so the goal at this point really is to construct those incentives such that we can get people to contribute data in a way that will then allow us to curate the data. We've hired, we're in the process of hiring a dozen linguistics undergraduates and graduate students to check every single speech sample to make sure that if it's read speech, that it contains the read speech, and if it's spontaneous speech, to transcribe what they said, so that we can then distribute the data with some performance guarantees. So the results so far: the software is under development. It will be distributed open source. The prompt lists will be distributed open source. The terms of the IRB. One of the things that we're not doing is collecting any medical diagnostic information at all, and this is because of concerns that that if we tried to collect medical diagnostic information in a half-baked way, that people would use our half-baked medical diagnostic labels as if they were gold labels. And so in fact, we've been sharing terms of our IRB with the NIH-funded Bridge to AI program, where they're collecting a large amount of data together with diagnostic information from the doctors as a way of promoting automatic diagnosis. And then we're working with advocacy organizations we meet with them almost weekly in order to sort of work out these IRB issues as I described. So we're hoping to be able to distribute 200 hours of transcribed speech from Parkinson's, ALS, and hopefully 3 other etiologies within a couple of years from now, with the idea of basically solving this problem, of making it possible to recognize the speech of people with disabilities related to age and with other disabilities, as well as we recognize the speech of anybody else. That's the current project. So just to kind of to conclude then, I think that Mitch Marcus's paradigm really does kind of carry to a large variety of social groupings. In multilingual training, we have monolingual pre-training works for a small number of languages. Multilingual phone models allow us to transfer knowledge effectively from well-resourced languages to under-resourced languages that we know about. Unsupervised ASR may make it possible to recognize speech in a language that we didn't know about at the time that we were designing the systems. For inclusive ASR, we certainly are able to recognize speech now in groups that are the society calls normally abled. We're trying to find at least ways of collecting the data that will allow us to figure out what the knowledge representations are that will allow knowledge transfer. We don't have that yet. And I think we're really not even at the point of being able to ask the question of what is the paradigm that we should break in order to be able to eliminate the idea of disability and recognize every individual with equal accuracy. All right, but that's where we are right now. And thank you.
Thank you so much, Mark, for this great presentation. Any questions?
Thanks.
Thank you, Mark. So you put as a goal a couple of slides ago, being able to recognize the speech of people with some kind of dysarthria at the same error rates as people who sound like audiobook narrators, which I guess is me. So is that superhuman performance?
That would be.
Or maybe it's not superhuman because maybe humans who are used to that particular speaker or that particular class of disability, speech disabilities, are actually able to match performance already. Do you know? Yeah,
that's it. So I didn't actually put in text that we want to match the performance that we get on audiobook narrators because I'm not sure if I want to commit to that being even possible. But certainly you bring up the point that that if somebody is familiar with my voice, they can recognize it much better than if I have a disability that causes my speech to be unintelligible to people I meet on the street, nevertheless, people who know me well will be able to understand my speech in most conversations.
One such disability is being 2 years old, by the way.
Yes.
So, I go back and I listened to recordings of my kids when they were 2, and we subtitled some of them, and thank God, because I
totally can't understand them now.
Yeah. Right, but at the time I understood them perfectly. So basically what I'm wondering is, have there been studies of, say, spouses, caretakers, whatever, of people with speech disabilities, speech disorders, to determine whether getting this kind of error rate is conceivable with enough personalized training? Or whether it's possible for humans, I guess.
Yeah,
I shouldn't comment on
what has clearly been shown in peer-reviewed studies is that you can dramatically drop the error rate. Whether you can actually achieve a 2% error rate has not been shown in any study. That may not be possible, but you can reduce the error rate by at least a factor of 2 if you have familiarity with the speaker. Yeah.
So a follow-up question, and sorry, there are probably other people who have questions. And actually, yeah, maybe I should.
No, go ahead. Like, I think we can stay like 5 more minutes easily. It's already fun, but
does anyone else have an important question? All right, I'll ask the follow-up in that case. But think about what you're going to ask next. So are there other kinds of accommodations that we can make? Like, suppose my speech is so bad that it's always dictation. The way we do it today is always going to be unusable. So the error rate is just so high that I would rather type or something like that. Are there other kinds of interfaces that could still make use of my speech without assuming that it's going to be transcribed on the first shot the way we might assume for an audiobook narrator?
Yes. So usually people for whom this, so in the past, this has been a very effective method for people with cerebral palsy, for example, because often if you have cerebral palsy, often you can't type, you even have difficulty with buttons. Yep. And so the ASR might recognize your speech, might only be able to recognize 5 distinct words coming out of your mouth. But having those 5 words available to you as commands might be tremendously useful. I spoke to one.
Because they become up, down, click.
Yeah, I spoke to one man, for example, who uses speech recognizer to open his wastebasket because it's very difficult for him to reach out of his wheelchair and to somehow get the wastebasket to open and to put a piece of paper into it. It's much easier for him to be able to say trash can open, and then even if a person from Starbucks might not recognize that, his ASR does. Yeah. The other thing that I've discovered is that some of these populations actually have remarkably technically literate people who have been doing things like this for the past 50 years already for themselves. And what we don't want to do is to sort of make it available to the people who have these disabilities who are not that technically literate.
Okay, we have 3 minutes left.
So what about the non-native speakers? So,
yeah, that would be a neat problem to work on, wouldn't it?
Yeah, because I know that Alexa has some problems understanding his learning. So I think both of us, right?
Yeah. I think that's sort of in this, in this knowledge transfer case. I mean, we're for all of these million speaker categories, right? It should be possible to collect enough speech that we can figure out what are the similarities between Arabic accented English and general American English, and we should be able to build a model that will transfer knowledge from the 50,000 hours of the multilingual liver speech to the 500 hours that we might have of Arabic accented English. I think that's possible. We haven't done it yet.
Well, this is the chicken and eggs problem.
Yeah.
In order to learn this difference between this Arabic, whatever accent or whatever accent English, you need sequences often of the data. Mm-hmm. When you initiate the data to learn it, you train on it and you're done. So what's the that's the question. Like the chicken and eggs problem.
Well, but it's not that because it's
like the 2 speaker, 3 speaker, and I will learn what the difference between my accent and Paula accent. You need a lot of consequential speakers to normalize that fast.
Yeah. Yeah.
When someone uses the point, it's like, I have no that I get to try on it and I'm done.
We might already be at that case, but if we are already at that case, it's because of self-supervised learning, right? And until self-supervised learning, I would have said that the other problem that we have is that we don't know what information can you take from the general American English corpus that will actually be useful in the recognition of Arabic accented English. We didn't know. And maybe self-supervised learning has already solved that problem. Maybe the answer is we do take the XLSR model and fine tune it on your 10 hours of Arabic accented English. I don't know. I would say that there's sort of two problems in this middle range of the Zipf's law. We have these two problems. One is, can we get data from those smaller groups? And second, we know that data won't be as large as the data set for the background for the general American English. Can we figure out how to transfer knowledge from the well-resourced community to the under-resourced communities? And the knowledge transfer problem is the interesting technical problem. That's, for example, the problem that we haven't even started to think about how to solve when we talk about disabilities.
Okay, so I think we need to leave. Thank you very much, Mark.
Thank you.